Hello dear students, this is Rita, Assistant Professor from Government Girls College, Bodiakheda, Fatehpur. In this video, I will discuss the important topics in the unit polarization. The topics name double refraction, Nicol Prism and Huygen theory. We will discuss all these three topics in this video. In my previous video, I have told you about the double refraction. What was the double refraction? When a ray of light is refracted by a crystal of calcite, it gives two refracted rays. This phenomena was known as double refraction. We have already discussed this phenomena. So we can say when a ray of unpolarized light is passed through any doubly refracting crystal like calcite, it will split up into two rays, E ray and O ray. Right? E ray is extraordinary ray and O ray is the ordinary ray. Now we will discuss that how the polarization is done by the double refraction. So in order to discuss this, what we will do, we will demonstrate it by sending a beam of light normally through a pair of calcite crystals, and then we will rotate the second crystal about the incident ray as axis. As you can see in the picture, in the figure A, I have used the two calcite crystals. So, when the principal planes of these two calcite crystals are parallel to each other, then the two images E1 and O1, they are seen. You can see here. The O ray from the first crystal will pass undeviated, and the second through the second crystal it will emerge out as O1 ray, and E ray from the first crystal passes through the second crystal along a path which is parallel to the first, and it will emerge out as E1 ray. Hence we will get the two O1 and E1 rays. So the two resultant beams or the images O1 and E1, they will be obtained and they will be separated by a particular distance. So that distance will be equal to the sum of displacement which is produced by the each crystal, right? Now you can see that in the second case, if we rotate the second crystal about the incident ray as axis, then the rays O ray and E ray from the first crystal each will split up into two parts, and it will give rise to the four images. So along with O1 and E1, we will get the two new images also named O2 and E2. So as the rotation of second crystal is continued further, then O1 and O2 will remain stationary, you can see, and E1 and E2 will rotate around O1 and O2 respectively. And what will happen with the intensity? The intensity of O1 and E1, it will goes on decreasing, and the intensity of O2 and E2, it will go on increasing. Now, when the principal section of the second crystal makes an angle of 45 degree, you can see in the figure number B that when the angle is 45 degree, then what will happen? The four images of equal intensity will be seen. We will get the four images O1, O2, E1, E2. They will be of equal intensity. On further rotation, when the angle becomes 90 degree, we again have only two images. Now, the original images O1 and E1, they will vanish out, and the two new images O2 and E2, they will acquire more intensity and they will appear. Right. Now, if we further rotate the second crystal, then the original images O1 and E1 appears again, and they will start gaining the intensity slowly. And the other two images O2 and E2, they will start fading slowly. Now at angle 135 degree as shown in the figure number D, the four images once again of equal intensity will be obtained. Now after, if we rotate it further, then at 180 degree rotation, the principal planes of two crystals are once again parallel to each other. But in this case, the optic axis oriented in the opposite directions. You can see in the figure number E. The images O2 and E2, they will vanish out now, and O1 and E1, they will come together, and we will get only a single image at the center. but this will be the case when we have that crystals which are of equal thickness. Now if we further rotate the second crystal, it means if we vary the angle from 180 degree to 360 degree, then these all changes will come again, but they will be in the reverse order. So in this, by doing this experiment, we have demonstrated that the polarization of the light by a crystal, and then we have detected it by the another crystal. Now if we want to explain this, that how the intensity of O1 and E1 is in first case it was maximum, and then on rotation it was decreasing, and then again it become maximum. So how it is happening, in order to explain this, we will go on the next slide. You can see here in the picture that I have taken AB and CD. If this AB and CD is representing the principal sections of first and second crystals which are inclined at an angle theta, then we can say that the ordinary light on entering the first crystal is broken into two plane polarized beams, as we have already discussed. So it was splitted up into one ordinary ray which was vibrating perpendicular to the principal section, and other we have obtained extraordinary ray which was vibrating in the principal section AB. So let us consider A is the amplitude. As you can see in the figure, I have shown here that A is the amplitude of ordinary and the extraordinary ray, which is represented by MO and ME respectively. The O ray, that is the ordinary ray, when it enters into the second crystal, then it will further split up into the ordinary ray and the extraordinary ray. So the ordinary ray will have the amplitude A cos theta, which is perpendicular to the principal section CD, and the another is A sin theta, which is the extraordinary ray, and it is in the principal section. So these amplitude here in the figure are represented by MO1 and ME2 respectively. So similarly, the E ray on entering the second crystal, it will also split up into an extraordinary ray of amplitude A cos theta and an ordinary ray of amplitude A sin theta. Right. So like this we have represented in the figure. So at finally you can say that the splitting of O ray and E ray on entering the second crystal is because of the fact that the second crystal, like the first, transmits the light vibrating in its principal section. Okay, now you can see that the intensity of O1 and E1 is A square cos square theta. You can see in the figure, and intensity of O2 and E2 is A square sin square theta. Right, we will discuss the special cases. That is what will happen when theta is equal to 0 or 180 degree. So at that time, this cos theta will be equals to 1 and sin theta will be equals to 0. So in this case, your I1 will be maximum equals to A square and I2 will be equal to 0, that is minimum. So you can say that O1 and E1 will have the maximum intensity and O2 and E2 will disappear at this time. Now the second case is when theta is equal to 45 or 135 degree. So if I substitute the values, I will get cos square theta and sin square theta equals to half. It means that O1 and E1, they both will have the, and O2 and E2 all will have the same intensity, which is equals to A square by 2. Right. The next case is that when theta is equals to 90 degree. At this particular situation, cos theta will be equals to 0 and sin theta will be equals to 1. So I1 will be equal to 0 and I2 will be A square, that is maximum. So we will say that O1 and E1 will disappear and O2 and E2 will have the maximum intensity, which is equals to A square. So we can conclude here that at all the positions, the sum of two components means I1 plus I2 will remain equals to A square. So plane polarized light will be gainfully obtained by the double refraction. Right. So, but one thing more here, I want to explain that why the two images O1 and E1 at 180 degree coincide and light emerge out as a single beam. So in order to explain this, we will say that the O ray travels through both the crystals undeviated, but whereas the E ray experiences equal and opposite displacement in the two crystals. So therefore images O1 and E1 coincide to give the single image at the center. So this was the reason that why O1 and E1 coincide at 180 degree. Now the next topic is the Nicol prism. Nicol prism is an optical device. It is made up from the calcite crystal and it is used in many optical instruments. It can be used as the analyzer. It can be used as the Polaroid. Right. So I will first discuss the principle of Nicol prism. Nicol prism principle is based upon the phenomena of double refraction. Means when the unpolarized light passes through the calcite crystal, it splits up into two rays, O ray and E ray. One is having the vibrations perpendicular to principal section and one is having the vibrations parallel to the principal section. Right. So both these rays, that is O ray and E ray, they are plane polarized but they are normal to each other. In order to obtain the single polarized beam from the Nicol, we should eliminate one. So Nicol prism is made in such a way that the O ray, that is the ordinary ray, gets eliminated internally by the total internal reflection, and only E ray, that is the extraordinary ray, will emerge out through the prism. So this is the principle of Nicol prism. So we can see here that the O ray will get TIR and it will be eliminated, and we will get the E ray only as the emergent plane polarized beam. You can see here in the figure I have shown that Ne, No and N blasm, that is the refractive index for extraordinary ray, you can see 1.4884. For ordinary it is 1.6584, and for Canada plasm layer which is in between, that is 1.526. Okay, so it means the refractive index of ordinary ray is more than that of the Canada plasm layer, and of extraordinary ray it is less. We will discuss this point later. So we will talk about the construction of this Nicol prism, how this Nicol prism is constructed. So Nicol prism is made up by taking a rhombohedron of calcite whose length is 3 times its thickness with optic axis in the plane PQRS, as you can see in the figure. Now you can see that here the end faces this PQ and this RS, they are making the angle of 71 degree and 109 degree. But in order to have the special construction for the Nicol prism, these end faces, that is your PQ and RS, having the angle of 71 degree and 109 degree, they are ground away until they make an angle of 68 degree instead of 71 and the angle 112 degree instead of 109 degree. So the resulting crystal we get after this is then cut apart into two pieces along the plane. You can see in the figure, along the plane P dash S dash, which is passing through the blunt corners, and also it is perpendicular to the both the principal planes. Now the two cut surfaces, they are grounded and they are polished optically flat. So we have the transparent substance which is having the refractive index midway between the refractive index of ordinary and extraordinary ray. I have just told you that a material which is having the refractive index midway between O ray and E ray, that is known as Canada plasm, we use that material here. So that material is used here, and these two pieces, they are joined by using that material. So the two end phases of the prism are kept open, while its sides, they are coated with the lamp black and they kept covered by a brass tube. So this was the construction of the Nicol prism, and we get a specially designed Nicol prism through this. Now we will discuss the working of the Nicol prism. So what will happen in the Nicol prism, that when an unpolarized light is made to fall on the Nicol, you can see in the figure also, then due to the double refraction, it splits up into two plane polarized rays, that is E ray and O ray. Now, as I have already told you that Nicol prism is specially designed in such a way that O ray is having the maximum refractive index and E ray is having the minimum, and Canada plasm layer is having the midway refractive index of these two. So due to this, the O ray will be totally internally reflected at the Canada plasm layer and it will get eliminated, and only E ray will be transmitted as the plain polarized ray. So we can say that as the ordinary ray is traveling from the denser medium, means calcite, to an optically rarer medium, means the Canada plasm, and it will suffer the TIR, that is total internal reflection, provided the condition is the angle of incidence at the Canada plasm layer is greater than the critical angle for the two medias, that is for calcite and Canada plasm. So this totally internally reflected ray is absorbed by the blackened side of the crystal, and the extraordinary ray under the same conditions would be transmitted on the other side, right? So the angle of incidence on the Canada plasm layer depends on the angle which the edge QP dash makes with the blunt edge and the ratio of breadth to length of the crystal. So that is why these two conditions should be taken into mind so that the O ray could be eliminated by the TIR. So that is why for this reason the natural angle of 71 degree was reduced to 68 degree and the length of the crystal was taken about 3 times of its breadth. So that the condition of TIR could be fulfilled. Now, along with this, there are some limitations of this Nicol prism are also there, that when the incident beam is slightly convergent or slightly divergent, then if then only we can use the Nicol prism, because if the incident ray makes an angle such that the ordinary rays strike the Canada plasm layer at an angle which is less than the critical angle, so it will be transmitted. It will not be eliminated in that particular case. So it should be kept in mind that when the ray is incident, then it should be slightly convergent or slightly divergent. So therefore the light emerging from Nicol prism will not be plane polarized in that case. And the second is that if the incident ray makes an angle greater, then the E ray will become more and more parallel to the optic axis and its refractive index will increase, and it will also get eliminated due to the TIR, that is the total internal reflection, and nothing will come out, nothing will emerge out from the Nicol prism. So we should use slightly convergent or slightly divergent light for this Nicol prism. So Nicol prism, we cannot use highly convergent or the highly divergent beam. So with the chosen dimensions, we can say that the angle between the extreme rays which we use for the incoming beam is limited to nearly 28 degrees. Okay, so this is how we can obtain the plane polarized light with the help of the Nicol prism. Now the next is the uses of the Nicol prism. Nicol prism could be used as polarizer as well as analyzer. So in order to understand this, we just read these points, that in order to produce and analyze the plane polarized light, the prism, two Nicol prisms are arranged. So when an unpolarized ray of light is incident on the Nicol prism, first Nicol prism, then the ray emerging from the polarizer is plane polarized, which is having the vibrations in the principal section of the polarizer. And if this ray is made to fall on the second Nicol prism, which is acting as analyzer, whose principal section is parallel to the polarizer, and its vibrations will be in the principal section of A, hence the ray will behave as the E ray in the prism A, that is in the analyzer, and it will be completely transmitted and the intensity of the emergent light will be maximum. So you can say that when a beam of unpolarized light is incident on Nicol prism, emergent beam is obtained as PPL, that is the plane polarized light. Since it is E ray, so it is having the vibrations parallel to the principal section. So this first is known as the polarizer. Now if this polarized beam obtained from the polarizer falls on the another Nicol prism, which is acting as analyzer, whose principal section is parallel to that of the polarizer, then incident beam will behave as E ray and it will get completely transmitted through it. So in this way, the intensity of emergent beam is maximum. You can understand this phenomena also with the help of this figure. I have explained the figure number 1, that is polarizer and analyzer having their principal sections parallel to each other. In the second case, if we rotate the analyzer, that is if one of the Nicol is rotated, then intensity of the transmitted beam will go on decreasing, and finally no light will be transmitted when the principal plane of Nicol, that is analyzer, will become perpendicular to that of polarizer, as you can see in the figure. So we here discussed the Nicol prism as the polarizer and as the analyzer. Now the next topic I am going to discuss here is positive crystal and the negative crystals. So positive crystals and negative crystals, when we talk about the uniaxial crystals, means the crystal having the one optic axis, then uniaxial crystals could be categorized into two categories, that is negative and positive crystals. What are the negative crystals? This first point I will discuss a little bit later. I will go on the another points that in the case of the positive crystal, the velocity of ordinary ray is constant in all the directions, and the velocity of extraordinary ray will vary with the direction. It is maximum and equal to the velocity of ordinary along the optic axis, and it is minimum in the direction perpendicular to the optic axis. And the refractive index for extraordinary ray is more than that of the refractive index of ordinary ray, means mu E is greater than mu O, except optic axis, because along the optic axis the velocity of two rays is equal, so their refractive index is also equal, right? So quartz and ice, these are the examples of such type of crystal. Since the positive crystal, the ordinary ray is having the velocity in which is constant in all the directions, so we will say that the ellipsoid of revolution corresponding to E ray, which is ellipsoid, it will be totally contained within the sphere corresponding to O ray. With respect to O ray, we will consider the sphere, since it is having the constant velocity in all the directions, right? So now we will talk about the negative crystal. In case of negative crystal like calcite, tourmaline, we will say that the velocity of ordinary ray is same, that is constant in all the directions, that is same for both positive and negative. But the velocity of extraordinary ray, it will vary with the direction. It is minimum and equal to the velocity of ordinary ray along the optic axis, and it is maximum in a direction perpendicular to the optic axis. And the refractive index for extraordinary ray is less than that of ordinary, means mu E is less than mu O. So, but in this direction of optic axis, mu O is equals to mu E. So this was about the positive and negative crystal. You can see here in the figure that in positive crystal, the refractive index of E ray is greater than that of O ray. Means mu E is greater than mu O, which means VE is less than VO. Right. And in the negative crystal, here the figure A is showing the positive crystal. In this you can see that the ellipsoid, which is corresponding to E ray, is completely inside that of the sphere, which is corresponding to O ray. Now in the case of the negative crystal, you can see that the refractive index of O ray is greater than that of E ray, which means that the velocity of O ray is less than the velocity of E ray. In the negative crystal, we can see that the surface of revolution, that is the sphere, which is corresponding to O ray, is completely inside that of the elliptical shape, which is corresponding to E ray. So this was about the positive crystal and the negative crystal. Now the next topic is Huygen theory of double refraction. So what was Huygen's theory of corresponding to this double refraction is, he said that whenever we use the double refraction, then in that case the crystal produces two types of wavefronts. The wavefront which is corresponding to O ray, that is the spherical wavefront, because we know that the ordinary ray travels with the same velocity in all the directions. So the corresponding wavefront will be obviously a spherical shape. and the wavefront which is corresponding to E ray, it is of the elliptical shape, because we know that the extraordinary ray will travel with the different velocities in the different directions. So the corresponding wavefront will be elliptical in the shape. So summing up the Huygen's theory for uniaxial crystal, we can say that the incident wave disturb all the points on the face of the crystal on which it is incident. So every point on the surface originates the two wavefronts. One is ordinary and another is extraordinary. The shape of wavefront which is corresponding to ordinary is spherical because of constant velocity of O ray in all directions, and the shape of wavefront corresponding to extraordinary will be ellipsoid because it is having the different velocities in all directions. The direction of line which is joining the two wavefronts, that is sphere and ellipsoid, that is an optic axis. Here you can see that how the velocities of O ray and E ray propagates. You can see corresponding to this positive crystal you get the spherical shape, and corresponding to extraordinary wave propagation you get the ellipsoid, since the velocity is different in different directions. This figure is also explaining the same, that for the negative crystal sphere is inside the ellipsoid, and for the positive crystal the sphere is outside the ellipsoid. Now next topic which is very important again, because in order to explain the different Huygen experiences, in order to explain this experimentally, we will take a uniaxial crystal so that the refractive index of ordinary is greater than that of the extraordinary. So we will take the uniaxial negative crystal and we will discuss the different cases. So the very first case in order to illustrate the Huygen theory is that when the optic axis is in the plane of incidence and it is inclined to the refracting surface. So first I will discuss this figure A, which is having the oblique incidence. So you can see here in the figure that the BD is representing the trace of the plane wave front which is perpendicular to the plane of the paper, and it is incident obliquely on the upper surface of the uniaxial negative crystal, and this crystal is cut in such a manner that optic axis lies in the plane of incidence but inclined to the upper face of the crystal. So when the edge B of the wave front this strikes the surface, the point B on the surface sends two wavelets inside the crystal. One is ordinary and another is extraordinary. Now according to Huygen's theory, we know that the ordinary wavefront is spherical and extraordinary wavefront is ellipsoid. So we are considering the negative crystal. So we know that the sphere will lie inside the ellipsoid and they both will touch each other at a point which is known as optic axis. So we can see in the oblique incidence that the ordinary refracted wavefront is perpendicular to the plane of paper. Okay, so it obeys the laws of refraction and it lies in the plane of incidence. But here we can say that the refracted ray E is not perpendicular to extraordinary wave front. You can see in the figure that the refracted ray E is not perpendicular to the extraordinary wave front. So in general we can say that the laws of refraction are not obeyed by the extraordinary ray in this particular case. Now we will see the figure of normal incidence. What will happen in the case of normal incidence? We can see that when the wavefront meets all the points on the crystal, in the case what will happen that if we draw the tangents on the plane as OO dash and EE dash, if we draw the two tangents, you can see in the figure OO dash and EE dash to the spherical and the ellipsoid surfaces which are originating from the B and D, where the incident wave strike the crystal. So the plane through OO dash and EE dash perpendicular to the incident surface will represent the ordinary and the extraordinary refracted wavefront in the crystal, and BO and BE are the ordinary and extraordinary refracted rays. In this case double refraction is taking place, as you can see. Now the next case is that when the optic axis is in the plane of incidence and parallel to the refracting surface. You can see here in the figure A for the oblique incidence that a plane wavefront AB is incident obliquely on the upper surface XY of the calcite crystal, and this crystal is cut in such a manner that optic axis lies in the plane of incidence XY. Now the two secondary surfaces, that is the sphere due to O ray and ellipsoid which is due to E ray, they will touch on this line. The position of ordinary and extraordinary wave fronts, that is CO dash and CE dash, they are drawn in order to represent here. Now O ray and E ray will travel with the different velocities in the different directions. So we can say that double refraction is taking place. Now we will talk about the normal incidence. What is happening in the case of normal incidence? You can see in this case we have O1 and O2, E1 and E2. These are the positions of ordinary and extraordinary wave fronts at the same instant. They are parallel to each other. AO and AE. Also you can see here BO and BE. They are ordinary and extraordinary refracted rays. Although these rays are traveling along the same direction, but there is a double refraction also. So because these rays are traveling with the different velocities. Because of different velocities, a path difference is produced between O ray and E ray on emergence when they will come out, but there is no separation into the two beams. So this property is of this is used in the construction of quarter wave plate and the half wave plate. This is a very important property. Now we will discuss the next case when the optic axis is normal to the plane of incidence but it is parallel to the refracting surface. So this particular case is also shown here. I will first discuss the oblique incidence. In this case you can see here that the optic axis is shown by the dots and it is parallel to the surface but it is perpendicular to the plane of incidence, as both O ray and E ray surface, O wave and E wave surface, the figures of revolutions about the optic axis you can see here, they are drawn in the form of the circles. One circle is in the blue color and one circle is in the pink color. And you can see here that O ray and E ray, they will travel with the different velocities along the different directions. You can see here this O ray is having the vibrations perpendicular and E ray which is showing the vibrations with the red dots, that is in the plane. So this was about the oblique incidence. Next we will talk about the normal incidence. In this case normal incidence, you can see here that O ray and E ray, they travel in the same direction but with the different velocities, but also here no separation is taking place. So we will say that the double diffraction is taking place. It is also seen here that in the case extraordinary wave has the same velocity in all the directions in the plane of incidence. So it obeys both the laws of refraction as ordinary wave does. So both ordinary and extraordinary rays are following the laws of refraction for this case. The next and the last case is that when the optic axis is parallel to the surface of incidence and is perpendicular to the plane of incidence. You can see here in the figure that the optic axis is perpendicular to the upper face of the crystal. It is shown by the parallel dotted lines. You can see in the figure also. You can see that your CD and CF are the refracted wave fronts at the instant when the wavelet from B reaches C. B से C पर जब पहुंचा तो हमें CD और CF दो refracted wave fronts यहाँ पर मिलेंगे, and AO and AE are the ordinary and extraordinary refracted rays. You can see here the O ray and E ray travel with the different velocities in the different directions. So we can say that double refraction is taking place in the oblique incidence. Now we will talk about the normal incidence. You can see here in the normal incidence that the refracted wave fronts, this CD and FG, they coincide at all the instants, and the refracted rays AO, AE they also coincide at all the instants, and they travel in the same direction with the same velocity along the optic axis. So in this case there is no double refraction taking place. So this was all about the Huygens theory and the different cases illustrated with the help of a negative uniaxial crystal. So you do well, and thank you for watching this video. Thank you.